Hello everyone. In this video, I'll walk you through my complete Kaggle assignment 1, which was on flight price prediction. So the first thing I did was to import all the basic modules like NumPy, Pandas, Matplotlib, Seaborn, sklearn models, and Light GVM, as well as some metrics for calculating the scores. The second thing I did was to set the plotting style for Matplotlib and Seaborn. Now we move on to the step one, which was loading the data. We begin by loading the train and test datasets and find out the shape of both of them respectively, which comes out to be like this. The training set has 40,000 rows and 12 columns, while the test set has 10,000 rows. I immediately inspect the structure of the training data using the .info function to understand the column types and check for missing values. Now we move on to the step 2 of this process, exploratory data analysis. Next, I generate the descriptive statistics for numerical features. The average flight price is around 20,800 with a large standard deviation, which suggests that the prices are widely spread. Then I run a missing value analysis. Features like airline, departure, and days left have around 11% missing data, while stops and duration are missing slightly less. I also check for duplicates and I find none. So we don't really need to remove any redundant rows. Now we move on to step 3, which was handling missing values. For missing values in categorical columns like airline and departure, I filled them with the more of the dataset, while the numerical columns like duration and days left are filled using the median. Now let's move on to step 4, which was outlier detection. To clean the noise, I apply the IQR method to the price column. I identify and remove 14 extreme outliers, which is just the 0.03% of the data. This ensures that the model won't be influenced by unrealistic price spikes. Now let's move on to the step 5, which was visualizing insights. To better understand relationships, I created several plots, which include a histogram to show flight price distribution, a box plot to compare prices across travel classes, two scatter plots showing how duration and days left relate to price, and a correlation heat map for numerical features. These visuals help us see patterns that the model might learn. For instance, longer flights and last minute bookings tend to be more expensive. Now let's move on to step 6, pre-processing the features. I encode all categorical variables using label encoder. I ensure the encoder is trained on combined values from both train and test sets to avoid unseen label errors. I scale the numerical columns, duration, and days left using standard scaler, which is crucial for algorithms like SVR and KNN. Now, as you can see below, for step 7, I split the new data into 80-20 train validation set. That gives me about 32,000 samples for training and 8,000 for validation. Now we move on to step 8, is model training and evaluation. Here I train multiple models which include linear regression, ridge regression, lasso regression, decision trees, random forest, gradient boosting, support vector regression, and light GVM. For each model, I calculate the R-square scores for both training and validation sets, MAE and RMSE for validation, and overfitting as the difference between train R-square and validation R-square. The initial results were pretty promising since the random forest had the best validation R-square of 0.9802. Light GBM was second with 0.9724, and gradient boosting had a lower R-square of 0.9527. The one that performed the worst was the SVR regression, which had a negative R-square. Now we move on to the step 9, which is hyperparameter tuning. In this step, I performed hyperparameter tuning for three models, which were random forest, gradient boosting, and decision trees. You might ask why I didn't include light GVM. It was intentional because light GVM was already performed very well out of the box. Since its validation R square was already 0.9724, higher than the untuned gradient boosting, tuning would most likely not have made a significant difference. On the other hand, tuning the gradient boosting model was showing pretty huge improvements, so it was worth the effort. Since for gradient boosting, I went from 0.95 to 0.98 after hyperparameter fine-tuning. Now we move on to the final step, which was model selection. After combining the tuned and untuned result, the best model turned out to be the tuned random forest with an R-square value of 0.9806 on the validation set. So that's the model I selected for the final predictions. After that, I used the best model, which was random forest, to predict the final predictions and then submit it to the submission.csv file. And that concludes the end of my report. Thank you for watching.